when I went to sign the register, that was an event. Because you go to England, to London, to the Royal Society, and only the British can do that kind of ceremony. Now my wife insisted that she will go. I told her it will be just in the INSA also. When you become a fellow, what do? Somebody announces and then reads a citation and you take a certificate, that's all. He said, no, I would like to go. Then I was planning to go, all the new fellows at that time, go and sign a book that is more than 400 years old. When the Royal Society Fellowship started, you will see a signature of Einstein, of Newton, this kind of people. So at that time I even remembered which page they signed.
You have to wear dresses like with that coat, long coats and everything, and they had to rehearse with a gold pen and a silver pen before they really signed it. So in the morning there was a rehearsal ceremony, and he liked that silver pen, and after that during the ceremony they don't allow to take many photographs. So the event is, they have a rehearsal also, but the real event is where they bring the book from a vault, because in the air-conditioned vault they keep it, and then it will be brought in by an uniformed person in a silver salver and that system, and then with a big rods are there with flags mounted in this, and they will precede this and follow this, as if it is a king they are bringing. And then each one will go and then sign on that 400-year-old register with a pen. There are two pens there, which is about 100 years old, and with ink. Ball-pointed ones are not allowed, and so that the pages do not get crumpled or soiled, they will have a blotting paper on it. You can't have your hand on it, you sign. To do that, they had a rehearsal also earlier in the morning. One thing I know, at his very early age, he did a very well-known discovery on ionosphere. There's a layer. He and one of his friends, Dr. Sain or something, in Australia they have discovered that layer. It is called Mitra D layer, and it is often referred until now by many scientists.
That is, if you want to see what that ionosphere is doing, or can I predict it, what is it doing in communication system, what is it doing in the positioning of the aircrafts, or the delay it produces in certain other phenomena, a timing system. Here in this laboratory, or many other laboratories in the world, there is a standard time and frequency system. You use atomic clocks. How do you transmit that from one place to another? You always cannot carry the clock. That's many million rupees worth. So you transmit that time and frequency. When you transmit it, if it is a long distance, it will go through the ionosphere. Ionosphere will change it. I'll put a delay system there. How do you know how much delay? So how do you know when you receive the time, what is the real time? So you have to correct for the delay. Now, to do all these kind of things, you need a sort of a standard ionosphere for the entire world, separately for different parts of the world, say different countries, for different times, daytime, nighttime, for different seasons, and different periods of solar activity, which means 11 years. I'd like to mention that when I was working in the ionosphere laboratory of Professor A.P.Mitra, physics was then taught by three giants: A.P.Mitra, Meghnad Shah, and Satyen Bose. All three were fellows of the Royal Society eventually, and I don't think in the history of India there was any period anywhere in India where one has an opportunity being taught by such three giants. Certain new aspects were coming up as a result after World War II. The first major work I remember was when Professor Mitra attended the first conference on the ionosphere in America, came back and asked me whether I could do something about a new layer of this ionospheric region called the D layer, which was then emerging. In my field, ionosphere, these are two famous people. Radcliffe, during those days in the 50s, 60s, 70s, he was perhaps the most famous man. He was an FRS, but he never took a PhD. He was MA FRS. He was like that. And director of the Cavendish Laboratory in Cambridge. Weinig was the director of the Ionosphere Research Laboratory in Pennsylvania State University. The first post-war ionosphere laboratory, that is where I joined. He invited me to come and join him there. There is Penn State University, the main door. That is where I had been in the faculty at a very young age, 51 to, after Australia, 51 to 54. And then 54 I joined the National Physical Laboratory. This is the Penn State. Now the ionosphere, from a layman's point of view, if I explain it, it is like an ionized mirror in the atmosphere, upper atmosphere. It extends from around 60 kilometers to many thousands of kilometers. But the region I'm talking about is below 100 kilometers. And it was beginning to be studied, and there was very little experimental or theoretical evidence of it. So I wrote an article. I studied it, both theory and experiment. That was published in an American journal. Now that had quite an impact. In fact, as a result, I was offered a faculty position in the Pennsylvania State University, where for the first time an ionosphere laboratory was being set up. The first international laboratory ionosphere. Professor Weinig was the director. While I got that offer from the Pennsylvania State University, I had to move over to Australia for work. When I was selected for Australia under Colombo Plan, I was not tested on physics in the selection committee. It was people like Humayun Kabir was a member, then Tara Chand, historian, and a couple of other people. So I was interviewed on history and Bengali literature, only on that one. So interest changed, interest continues. I was offered a fellowship. And Australia was at that time beginning to work in a very major way on what is called radio astronomy, using equipments that were left behind, radars and other high-frequency equipments that were left behind after World War II. They were renovating them, modifying them to use radio noise from the galaxy, from the sun, from radio stars. There, an Australian scientist, C.A. Shane, and I decided to do something that was not done before. That is, use the radio noise or radio signals from the galaxy to look at our atmosphere. So because my interest was using radio waves for the ionized region of the atmosphere, and I saw that those techniques are not in a position to see anything above the maximum of the uppermost layer. That means above about 300 kilometers. So we want to know what was above us, above that height. That supposing I use radio noise from the galaxy, and then it's coming from outside. We'll use an equipment to receive it, and then from there we see the footprint of that signal. We did that, and in about 8 or 9 months' time we set up an equipment. We saw radio signals. We could explore the region that was not known at that time. Until the satellites came, that was not known. And we also discovered that it could be used as a very significant, powerful tool for looking at solar flares that periodically occur, that disrupt the communication systems. Those times you could have radio fade-outs. These are all from solar flares. And also, along with this solar flare, you have a magnetic storm from the sun. And that kind of disturbance in the communication system can last for a couple of days. So you could predict them, you could understand the mechanism. But the method we developed, we called the cosmic radio noise technique. Later, when it became very well known, it was used by many people in the world, and it was miniaturized also. The name came to be rheometer, and rheometer is a very well-known technique. So that was the period in Australia, and then I decided to go to take up that position in Pennsylvania State University, and so moved from Australia directly to Penn State. There, in that ionospheric center, they were at that point of time trying to get some of the best people in the world. Newfield and Marshal Nicolay, who became Baron Nicolay in Belgium, and then Rydbeck from Sweden, myself. We became not only faculty members and later on also their consultants. And the entire area of ionospheric chemistry started at that time by Nicolay and myself in that university. Then when we set up in a few months that cosmic radio noise technique, that is using galactic noise from the galaxy to look at our atmosphere in Australia, we set it up in a few months, and that was a big moment. So when we first got the signal. At that time, I was asked to be one of the delegates from the Indian side. And the senior people who came was A.P.Mitra and Krishnan from this laboratory. There I remember we met Appleton, Sir Edward Appleton, Nobel laureate. He was the man who discovered the ionosphere. And when he came to know this work on cosmic radio noise, he was very impressed. He immediately said that, why don't you send it to our journal? And so that was the international journal from England that he had brought up there. So when I first wrote my D-Region paper that created some kind of a spark in America, and as an university PhD student, and when I found that then one of the best-known journals there not only published it, they published it with a comment that will give all the reprints he wants free, that kind of system. For a young student, that was a big moment. When I went to Australia, the first international meeting I attended was that of the International Scientific Radio Union General Assembly. That was in Sydney at that time. Also, when I was in Penn State in the initial period, the very first international conference on the D region came up in Switzerland. This was an interesting experience with Father Luzon. Luzon was the discoverer of flare-based system called atmospherics. He was looking at atmospherics. He found an increase in flare. Now, I had just joined Penn State at that time, for my work on D region. And at that time, Luzon wanted to have an international D region conference in Switzerland. So that is where I was invited, and that is where I went by the US military plane. I was the only one carried there. And I was one of the chief speakers there. So Luzon was very old by that time. So most of the discussion went through his daughter. In Australia, I was there for about 10 months, and then went to America, then that university, came back here. So not only that, when I first came, this will refer to the practical application. The very first work that I was asked to do was by the All India Radio. All India Radio, at that time, it is radio broadcast, they were depending on forecasts of frequencies to be used in future from Australian and UK forecast systems. So that process took them time, 3 months to 6 months. So they asked me whether we could do the forecast for them, and that meant a forecast of solar activity. And we produced that forecast in a few months' time frame. And since then it is going on. So ionospheric forecast, later on another forecast came on tropospheric radar troposcatter system in the 70s. They are still being done by this laboratory. Can you see this one? This is a picture of our facility being built. One of the early experiments at the National Physical Laboratory. Before the International Geophysical Year, we were a very small group setting up the experimental facility that we had discovered, which is the question of using radio noise from the galaxy to look into our atmosphere. The idea behind it is, instead of putting a transmitter at the ground, which will then get reflected, the radio wave reflected from the ionosphere, which is the ionized layer, we wanted to use a natural transmitter. The transmitter is our galaxy. The IGY period, International Geophysical Year, 50 years back. I was a young man at that time. I was running the program, and there were problems. Some unexpected problems came up at some time. The ionospheric data came from Taiwan. Taiwan at that time, according to our rules, any material coming from Taiwan would be confiscated by customs and burnt. So they were confiscated by customs and burnt, and a postcard came to me saying that under rule such and such, this has been burnt. So I wrote to Finance Secretary saying that you cannot do it because these are ionospheric data. We are part of the International Geophysical Year. All data can be distributed all over the world. So change this rule. They changed it. So there was bureaucracy, but they changed it. I will give you a more recent example, Antarctic. The first Antarctic expedition. Look at the way the bureaucracy behaved. This laboratory's bureaucracy at that time. This was in 1979 or 80, or around that time, the first one, when Indira Gandhi was the Prime Minister. I was involved in the planning of it, but it was confidential at that time. The director of that laboratory didn't know. I was not the director, but I was involved. So I chose a person from here, a young person. I was asked to choose somebody. I chose one person, unmarried, young, and then told him that you get your family's permission on it. So he came and said he will do. Then I was told that he will have to go for training for exposure to high, very low temperatures, so in the Himalayan region. He will have to go by air frequently. Now, he was a young man and junior level. He didn't have, we could not permit him under the Government of India rules. You'll go by train, he cannot go by air. But I sent a note to our administration without giving any cause. I said, so and so, for the next couple of years, we'll fly by air at different places. You give him the money for that. They never asked a question. That was done. Later on, when the Antarctic expedition came successful, I asked them that I had thought that you might oppose it. He says, no, we realize there is something behind it. He will let us know later on. So if there is a trust, they will go along with you.
Well, the first expedition was a very exciting event for all of us that were a part of it. And I still vividly remember the days leading to it. You know, it was such a thing that at that time everything was a closely guarded secret. We were not even allowed to talk to our families about this thing. You know, it was such a close secret. At NPL, I think Dr. Mitra just called me to his room. We had just returned back from the previous RC General Assembly in Washington, D.C. And I think just a few days after that, I suddenly got a call from Dr. Mitra's office saying that he would like to see you immediately. And the first thing that came to my mind, oh my God, I have not written my report for the RC trip. That must be it. So I kind of, you know, with a lot of apprehension came into the room, and he says, hey, look, I want to talk to you about something very confidential. Let's close the door and let's, you know, and this should be purely between. And he says he wanted to play it very safe, didn't want to tell me Antarctica right away. He says we are talking about an expedition to southern Indian oceans. Yes, it's very uncertain. We have not been there before. Would you be interested? So, sure, why not? Although I've never been on a ship, I've never seen the ocean, but sure. So that's how it all started, and rest is of course history. This was way back in December 1981, so almost 24 years ago. And I was one of the youngest members, probably the youngest member in the team, so it was very exciting. 6th of December was the day that we got started from Goa, and the journey took us almost a month, actually a little more than a month, mainly because we attempted several landings. You know, I was talking about whether, you know, what's the big deal about landing in Antarctica? You just go and land, but you actually don't, because the sea alongside freezes considerable distance in winter. And only when the ice melts, breaks and dissipates can you approach the land. And that happens only in a few places along the coast. And if you're lucky, you hit one of those. That explains why all the Antarctic stations are kind of bunched together along the huge coastline spanning lakhs of kilometers. So, and none of us had any clue about all these minor details. So we went and wanted to land directly beneath India, directly southwards. So we went and got stuck in the ice, tried a little bit. Our ship was a very small ship, and we traveled a little distance, gave up. So we came back on open seas again, and then started moving westwards, attempted another landing. Again, the same story, got inside and came out. And the third time, the same thing again. And all the while, the younger guys amongst us with less patience were getting more and more impatient. At that time, somebody says, "Yaar, aise kar ke pura chakkar laga ke ghar jayenge." We'd probably never be able to land. So, but finally, about fourth attempt, I think we found this little channel where we had clear water, and right enough, we were close to a place where there was somebody already with a station, the Russians.
Now, what was the result of this IGY? IGY, we had program on ionosphere, we had program on cosmic rays, we had program on sun meteorology. The other event was, after the IGY, 3 people were selected by the President of the United States from all over the world at a senior level as a guest of the President of the United States. It was Kennedy at that time. I was one of them. I was one, Piggott from England was another, and Rydberg from Sweden. And now, during that period, as the guest of the President, he went to different places, and we found that many of these places had very high regard on that work of atmospheric chemistry that we did, because it was beginning to come up everywhere. It had influence on practical applications in the sense of military operations, in the sense of changing the ionosphere, modifying it. My field of work recently changed to a different field, from ionospheric communication. Then when the satellites came up, we went to space science, but using again radio wave. Space science, some of the early rocket experiments, taking payloads were done by us. Bikram Sarabhai, Professor Menon, myself were key people in the beginning of space science work. In fact, when this rocket range, Tumba rocket range, was proposed by Sarabhai to the UN Outer Space Committee to be one of the UN recognized rocket ranges, then I was asked to replace him when he was attending the meeting. He had to go off. He asked, that was Nehru's time, so he sent a message to through Baba to Nehru, and then I had just come back from Latin America and picked up my wife in Calcutta and my baby at that time. And then when I came here, I landed here, I was told that I have to go to Geneva for that meeting. And well, as I said, we were together in the beginning of space science, and much of the work at that time, from then on, including ionospheric chemistry, satellite systems, then that satellite drag, and many of the work we continued. We are increasingly getting interested in the radio remote sensing. See, when you remote sense, some of the things you will not be able to remote sense with the optical system. When there is a cloud, very heavy rainfall, you use a microwave system. But there are radio waves which see through the cloud. So why did you use this? The wave I'm talking about. Radio remote sensing. The remote sensing that is normally done, if it is cloud or rain, you have a problem. So when there is a heavy rain, there will be an attenuation. But if you are below 10 gigahertz, there are certain frequency ranges where even the rains are not that effective. So you can see through clouds. For example, disaster management. This can be used very effectively, this kind of a system. Although it is short range, it doesn't go beyond the radio horizon. Unlike, as I said, those frequencies which are propagated by the ionosphere. For example, Bangladesh flood, you should be able to use it. Or the total amount of water collection in some part, like Bombay, that kind of system, you could have used radio wave. So why did you use this? Or radio metrology, this time and frequency I mentioned. Every country needs it. But then they buy the equipments. So I suggested to an international body called International Center for Theoretical Physics. This is in Trieste in Italy. And it was set up by Salam, the Nobel laureate, originally Pakistan origin. So wherever you use the high frequency radio, you'll have to use this prediction. And the predictions, our measurements, these are now routine experiments. At that time, they were not routine. But the predictions come from here. And one of the things that we did in the early days was not only prediction of this, of the communication system, but the parameters that control communication, like the sun itself and its radiation, or the magnetic field. And we introduced a warning system, it's called Erzi-Gram warning, that still continues. And it has suddenly come up as a very important event because a new program is coming. I'm now crossing time barrier. From there I'm jumping because I want to show you how things appear in a new garb, a new avatar. So what was ionospheric chemistry came as atmospheric chemistry, planetary chemistry, and now global environmental chemistry and climate change. What started as a component of communication prediction to look at the sun for communication purposes has now re-emerged as a new activity called causes, climate and weather in sun-earth system. The idea behind it is the changes that you see in the atmosphere. Some of them are periodic, some are irreversible, it looks, some are man-made, some are natural. I'm now talking about the contemporary world. At that time, there was a feeling that India is emitting a lot of methane from its paddy field. It came out in the Intergovernmental Panel for Climate Change. And the first report was coming out. In that it was mentioned. It was an estimate from the United States Environmental Protection Agency. And there was a pressure also, political pressure on India at that time. So I decided to check on that one. And so I had retired as the Director General. I came over here. And then we mounted a program, got several people in, several institutes and universities, and completed the entire campaign in 6 months with a grant that was given to us on telephone by the Minister of Environment. And that showed that the emission is 1/10 of what they were talking about. So they didn't believe it, we had to fight it, we fought. Even Paul Crutzen was skeptical about it. He says, look, Mitra, you are becoming a political animal now. But then we said, you come and check the values. And so net result was, as a result, many other countries like China, Thailand, who are also large emissions, they started operating, measuring. We gave them training. Sometimes we give them equipments. There were 3 or 4 international training programs we did. Net result is, this entire global emission from paddy field is now estimated to be something of the order of 1/4 of what was believed at that time. So it is no longer a problem. In fact, we are still continuing measurements of that, and we have something like 10 years of measurements. It confirmed our early estimate. So that is considered a very important work in both politically, from Indian point of view also. Indian point of view, it created an opportunity for India to, in the not controversies, in the debates of climate change and global change programs, to have its own line. One line is, we have to make our own measurements, we have to make our own decision. Second line is, don't attribute too much of emission from us, because we are a low emitter. So look at this. This is one. Second one we did was, which has many important outcomes, is the what is called the Indo-X program, Indian Ocean. The whole idea was, when you talk about climate change, we talk about greenhouse gases, carbon dioxide, methane, into long lifetimes, global. But there are other things, like aerosols, particulate material. Their climate forcing aspect was not very well known, and what the composition was not known. So we planned a program over the Indian Ocean in winter. The whole idea was, the winter, the monsoon flow is from the land to the ocean. It goes the other way. And we decided that at that time, we'll record measurements through shape, through aircrafts, and other means, through satellites in the Indian Ocean, and then look at how much of these pollutants, particulate pollutants and gaseous pollutants, are coming from the Indian land. So that was the famous Indo-X program. This showed one very surprising result, that there is a lot of it. It can change the climate in winter, change the rainfall, but also it showed what we call the brown haze, that Asian brown haze. And brown haze is a result of black carbon that is being emitted. That black carbon comes from low combustion, biomass burning, or low level combustion of coal, or inefficient vehicles. Now, net result of this, it has both many practical as well as political significances. As a result, now a global program has been initiated. It's called atmospheric brown cloud. It is no longer Asian brown cloud. It is an atmospheric brown cloud in a global sense. So Japan has joined in, China has joined in, Korea has joined, and Maldives is one station for intercomparison. That at that time, our interest was in terms of the changes of the ionosphere. That means in terms of the communication system, radio communication system. Now, we found that the critical parameters that control these changes are often not the major constituents. What we call trace species, like nitric oxide, ozone, atomic oxygen. But our interest at that time was mostly on nitric oxide, because nitric oxide produces this region, the D region that I mentioned. And so the role of small trace species means that you can manipulate them. So this question of manipulating the ionosphere came up at that time as a part of defense system, as a part of communication changes. And so, for example, you can create a hole in the ionosphere by having a high power radio wave, or you can inject through the rocket systems some compounds that will produce a hole in that region. All that will come from these little small number of molecules. An active satellite can be totally I would say it is not dislodged, but it can be put out of action by this space weather. Space weather is essentially that ionized atmosphere is being changed, and you are putting in a lot more ionization from the sun. So the whole idea here is not limited to, focused primarily on two regions of the atmosphere. One is the upper one, which is dominated by space weather. The second part is the lower atmosphere, near the Earth's atmosphere, the climate change, and it can be gradually it can be competitive. That is when the Kyoto Protocol Framework Convention takes into effect, and methane emission, Montreal Protocol, ozone, all of these come into effect gradually. And then when the global change came up, this whole chemistry science came to the lower atmosphere. But not only that, it moved on to, when you look at the chemistry, right down the time, even now, it is holding perhaps the most critical position in many of the topics relating to human society, like global environmental change, climate change, is a result of this atmospheric chemistry. We did the ionospheric chemistry at that time. That moved over to planetary chemistry when the satellites came up. So planet science, Mars, Jupiter, Venus. So to understand what kind of atmosphere there will be, you look at the chemistry. IGY, we had program on ionosphere, we had program on cosmic rays, we had program on sun, meteorology. There were many programs of this kind. But at that time also, the first solar density model were given. And A.P.Mitra gave one. We gave one from the satellite system, satellite drag system, immediately after the satellites came up, a little after IGY. In fact, that became the basis for satellite drag calculations, like the satellite lifetime drag, etc. And this satellite drag system is based, as I mentioned, on the atmospheric density. So all atmospheric density calculations are based, primarily started with either A.P.Mitra's model or our model and that system. You know, when I met A.P.Mitra, I had not, and to join his group for PhD. My results have not come out at that time yet. And I was interested in joining psychology at that time, and rather than physics. And so, although I had appeared in physics BSc examination honors, so I went to the head of the psychology department. He says, yes, immediately you can join me. But he called up Professor A.P.Mitra, then asked him that here is so-and-so who has come to me. Now, why did you release him? Then A.P.Mitra came to know, and he called me. He says, no, you don't join him. You join me. So I will give you a scholarship right now. So even though my degree, the result had not come out, so I joined him. And he was a superb professor. And now he could tell you, this is the learning process. Now you do an experiment or a calculation, you bring it to him. He will immediately say no, without doing that, or yes. Now, how does he say no? Because that result doesn't correspond with or check with something else he knows. So it is not necessarily that particular field. So we learned that way. And then another one, I don't know whether I will go into it because it costs a lot of money and a lot of effort. I have been talking with Department of Space on that. It's solar powered satellite. Power is going to be a major problem. So how do you go alternative power? So you are going with the wind power, solar photovoltaic, solar thermal, etc. Hydrogen, this laboratory is interested in that. But there is another one. You capture the solar heat in a satellite, transmit it in the radio frequency to the ground, and then redistribute it. That's the Japanese are doing it now. My friend Matsumoto that I mentioned here, with the Japanese electricity companies, are trying it out. And solar power satellites, we have almost all the components here. We have the satellites, we can make the antenna systems, that's radio science. Transmission in the microwave, we can do that. The effect of microwaves on the atmosphere, we can study that. And then ground-based systems, distribution will be electrical systems. So we have all the components. Doing in positioning of the aircrafts, or This is one of such timing system. The party you have to leave it. আপনি ক্যালকুলেশন করেছেন